Welcome back. We've just shown that we got too many equations just using a straight Kirchhoff's uh, loop analysis methods. We ended up introducing extra variables. It looked like we were going to have it probably around 8 variables, just way too much to deal with, especially in the context of an exam. So what we're going to do is now we're going to use superposition. Again, we're going to end up detaching this circuit since there are no current flows in the ideal case into an op-amp, so this current should be 0. We're going to turn off the active current source. Recall that we cannot turn off any dependent sources. We've got to keep those in the circuit. So here we go. Let me redraw this circuit without this current source. Remember, this current source is going to become an open circuit. So we've got R6, which is the 1K. So we've got this situation. All right, let's see. Okay, now the question is, I just noticed this, is this marked as V1 as a variable, or does it indicate that it's the same as this? That's interesting. I'm going to assume that we don't know that. Okay, not sure why that's up there. Alright, so this is the circuit we have. I'm going to ignore this piece. I'm going to introduce two currents, IA and IB. And so we'll do our regular loop analysis. So in this case, we've got 0 is equal the voltage drop, which is negative V1, plus current goes through here, the voltage drop through this resistor is negative Vx. Then here the voltage drop in this direction, we've got to take the current IA, but there's a current opposing it, so it's minus IB times the resistor through it, 1K. And then through here we've got a voltage drop equivalent to IA times 4K. So the second loop gives us, let's start here. So we go in this direction. So we got a drop which is IB minus the current opposing it, which is IA, times the resistor, 1K. Then we go through here. There's just one current there, which is IB times the 2K for the resistor. And then it goes through here, and then we've got a voltage drop of an unknown voltage. Let's call this, I'm going to call it V2. So our IB current is going through here, so there's a drop in the direction of IB, which is 0 minus V2. So let's see how many unknowns we have. By the way, V1 is a known, which is 3 volts. Let's see, so we have 1, 2, 3 unknowns, so we need another equation, which I think we can generate right here. So we know that Vx, let's see, the current's going in this direction, so negative Vx, so the drop would be negative Vx is equal to the current Ia times the resistor. And there we go. So we could actually replace Ix right here with this, and then have two equations, two unknowns, and we should be able to solve straightforward. So let's do that. Let's rewrite this top equation. We'll bring V1 over. V1 is equal to negative Vx is equal to Ia times 1k plus Ia 1k minus Ib 1k plus Ia 4k. We can combine like terms. We've got Ia 2, 6. So Ia 6k minus Ib 1k. One equation there. Next equation, let's see. I think we made a mistake right here. We don't multiply the current times the voltage drop. So right here, we've got it's just the voltage drop we're looking for. So from here to here is negative V2. So we do have another unknown, V2 right there. We will need another equation. So let's take this one. Let's bring V2 over. So we got V2 is equal to Ib 1k minus Ia 1k plus Ib 2k. Simplify. V2 is equal to minus Ia 1k plus Ib 3k. Almost there. So we have the nasty unknown V2 that we'll need to get another equation for. Let's see what we can do. Well, we call this, we give this a node. Let's call this, well, maybe that's why this was there. Let me pause the video. Okay, I think I realized the issue. It's actually pretty simple. So if we go back to our modified diagram, we can see that negative Ib must equal this current, and that'll help us get rid of our unknown here, our unknown V2. We already know what Vx is in terms of the unknown. So what we'll do is we've got to replace Ib. So here are our equations so far. Again, we got this equation by simplifying our first equation. We got this next equation by simplifying our second equation. And we were stuck because we had three unknowns, Ia, Ib, and V2. So we're going to replace Ib. So we know that negative Ib must equal this current, which is 4 times 10 to the minus 3 Vx. And we know that Vx is negative Ia times 1k. So 4 times 10 to the minus 3 negative Ia 1k and and the negatives cancel, and we get IB is equal to 4 times 10 to the minus 3, IA 1K. The 1K and the 10 to the minus 3 cancel, so we have IB is conveniently equal to IA times 4. So let's go plug that in. So let's plug into this first equation. V1 is equal to IA 6K minus IA times 4 times 1K. And so we have V1 is equal to IA 6K minus 4K. So IA 2K. So IA is equal to V1 over 2K. V1 is 3 volts if you look at back our original diagram. So 3 over 2K, which is equal to 1.5 times 10 to the minus 3 amps. For IA, and remember, ultimately what we need is the contribution to Vx. So we have that relationship right here. So IA is 1.5 times 10 to the minus 3 times 1K. The K, 10 to the 3, cancels the 10 to the minus 3, and so we're left with 1.5, which would be volts, is equal to negative Vx. So Vx is actually equal to negative 1.5 volts. And that's due to the contribution just of this active source. So let's stop there, and then we'll turn this source off, we'll turn on the current source that we removed, and we'll do it again.